All right, I want to take a look at how do you actually solve problems involving projectile motion. So the first thing I want to remind us of are some of the assumptions for projectile motion, because keeping those assumptions in mind helps us narrow things down. So remember that in the horizontal, our acceleration is 0. So what that means is it means our horizontal velocity is constant at all times. So Vx0 and Vx are the same thing. Also, our acceleration in the y direction is constant and it's equal in magnitude to g. And depending on how you set up your coordinate system, that might be a plus or a minus g. But that is constant. It doesn't change at any point in the path of the projectile. It's always there and it's always pointing towards the ground. We assume with these assumptions here that makes this true is that the only force acting is gravity. So there won't be any air resistance. We have to assume that time starts after the object leaves the hand of whatever's launching it, and that time stops before it hits another object, at the instant right before it hits, so that we can't have any other things acting on the object besides gravity. We also have to remember that if we have a horizontally launched projectile, has an initial velocity that is equal to 0. Vertical initial velocity that is equal to 0, and the initial velocity is equal to Vx0. So that could be any situation, like a ball rolls off of a table, or I throw the ball just horizontally. In those cases, those have to be true because theta is measured from the horizontal, so theta is equal to 0 in either of those cases. So therefore you can have no initial y component. It doesn't start to gain a y component until after t0. The other thing we have to remember is that at the top of the path, that the vertical velocity is equal to 0, but our horizontal velocity is still equal to whatever initial velocity is. So if it's thrown at any sort of angle or anything at the top, only the y component is equal to 0. There is still a horizontal component. And that's different than when I tossed a ball straight up in the air, when at the top the overall velocity was equal to 0. And that's because there was no horizontal component to keep on going. So those are kind of our assumptions. Now let's take a look at those kinematic equations and how our assumptions will come into play. So in the horizontal, we have Vx equals Vx0 plus AXT, x equals x0 plus Vx0t plus 1/2 AXT squared. Writing these down over and over again really helps you memorize them so you make less mistakes. I know they are on the formula sheet, and you should always double check the formula sheet if you're unsure, because I always see people mix and confuse the equations together. I'm just going to use the delta x version here. And I'm not going to do the fourth equation just because it doesn't have as much use in projectile motion. Actually, it has the same effect as using the second equation in the x direction. And then in the y, Vy is equal to Vy0 plus Ayt. Y is equal to y0 plus Vy0t plus 1/2 Ayt squared. Vy squared is equal to Vy0 squared plus 2Ay delta y. All right, so let's take a look at the x direction of our assumptions. Well, our biggest assumption is that our horizontal acceleration is equal to 0. So if I plug in horizontal acceleration equals to 0 into these three equations, you lose entire terms. And what ends up happening to the first and third equations is they just say Vx equals Vx0. That's all they tell you. They just tell you, hey, the velocity is constant. So the first and third equations in a projectile are basically useless. So the only equation you're really going to work with is the second equation in the x direction. So that really simplifies things down. Now, do not just, sub in and memorize what this looks like without that. subbing in and recognizing that your horizontal acceleration equals 0 is often a point on AP free response questions. So you always want to start with this fundamental equation as it is written and then go through and sub things in. Like, for example, my initial position is usually 0 as well. So this really just simplifies into x equals vx0t. And by the way, if you divide time, that just says speed is distance over time. So that's true just because the velocity is constant, so you're going at the same rate of change of displacement over time throughout the whole motion. So that's really all the x equations give us. Now, unfortunately, the y equations don't simplify down. But if we take a look at the equations, we can kind of figure out where they might be useful. So this first equation, it has the final velocity in it. That's usually not something we know in problems. It's very difficult to measure velocity straight up. So it's kind of the variable they often ask you to find. So if you know your initial velocity, you know your acceleration and time, this equation is good to find that y velocity, but it's not good for just about anything else. The only place where this might be useful is at the top. Because at the top, Vy is equal to 0. So this simplifies this equation down. So it's useful to find the time it takes to get to the top, given your initial velocity and your acceleration due to gravity. Same with the third equation. The third equation doesn't have time, which is really handy if you don't know time, but a lot of times you have to find time along the way. But it's also really useful at the top because Vy is 0, and this one appears useful for finding the time to get to the top. This one's really used to find the height at the top, given just initial velocity and acceleration. So those two equations are really more useful if you're looking for some sort of problem or you're learning about information at the top of a projectile's path. Now that leaves the second equation, which, what do you know, is the exact same equation we use all the time at x. So this equation is your best friend in both the x and y direction. Now this is unfortunate because our acceleration here isn't 0, so this is a full-blown quadratic equation. And sometimes you will have to solve the full quadratic equation. Other times, like if I'm starting at the ground and ending at the ground, my y's, my initial and final y's are 0, and then I can factor out a t and I can solve this without going through the quadratic equation. But there are times when you may have to go through the whole process. So it can get overwhelming, but that gives you a place to start. So if you're in doubt of where to start, first of all, sub in anything that's 0, and then the position equations with the t squared, that is your number one starting position if ever you get stuck. And then remember, if you're at the top, Vy is equal to 0, so the first and third equations become really handy. So let's take a look at an actual problem. Okay. So in this problem, this is a numerical problem, but we're going to work it primarily non-numerical because we can learn more about how projectiles work non-numerically than by just plugging in numbers. If we have this shell, like an object, is fired from the ground, so it's going to start here at the ground, and it's going to be fired up in a projectile path. And it's asking for the range. So the range is basically this x position relative to an x0 equal to 0. So that's ultimately what we're trying to find. We can define t equals 0 to be the time there that it leaves, and t to be the time that it hits the ground. Now we don't know any of that information. We do know that it's launched with an initial angle of 55 degrees above the horizontal. And then that initial speed is 1.70 times 10 to the third meters per second. And we could define y equals 0 to be the ground. Essentially what I'm doing by setting y equals 0 to be the ground, I'm defining the upward direction as positive. So I'm defining the acceleration in the vertical to equal negative g. So that's going to be a negative direction. Now what I can do is I can create a variable list from that information. Now, I usually have enough information just labeled on my picture that I don't need to do more than that, but it's a really good idea when you're getting started to practice going through the variable list. Ax, t, what did it say? V0 might be something. Y0, y, Vy0, Vy, Ay, theta. I think that's probably pretty good. So from the information that we already know, we know that our initial position is 0. Our initial vertical position is 0. Hey, our final vertical position is 0. We're looking for our range, our ending position. We know nothing about time. We have an initial horizontal velocity but it's unknown. So I can resolve this Vx0 and this Vy0 into components based on trig. I know that the horizontal component's the adjacent side, so that's going to be V0 cosine of theta. And then the y component's the opposite side, so it's going to be V0 sine theta. I don't know anything about my final velocity over here when it hits the ground in either dimension. Actually, I do, if I really wanted to. My final horizontal velocity is going to be the exact same as my initial horizontal velocity. And my final y velocity, we talked about this kind of when we analyzed it, is actually, because I'm going to the exact same height, it's actually negative V0 sine theta. And this is actually V0 cosine theta. So I'll be going the same speed. So actually the speed here at the bottom is exactly the same as the start. So the speed at the start is 1.70 times 10 to the third meters per second. And that's the same speed it is right here at the bottom, times 10 to the third meters per second. So that's kind of cool. That's more information than we need to know for this problem, and I'm not going to use it at all to like choose different equations, because I want to go through this in a very particular way to give you a demonstration of how to solve a system of equations when you don't know as much information. Because if this had been launched from a cliff, you wouldn't be at the same height when you hit the ground. So a lot like this assumption wouldn't work. It would work here, but not at the ground. So we just have to be careful about using those assumptions all the time. They're good shortcuts when they apply, as long as you apply them thoughtfully. The horizontal acceleration is 0, the vertical acceleration is negative g, and our theta is 55 degrees. So actually we know a lot of information. But for the purpose of this, I'm going to ignore these final velocities because that's extra thought that I would not normally put in. So I'm just going to kind of leave it with this. Now, the next thing I would do is kind of think about, what do I know the most about and what can I find? Well, I know a lot of information in the y direction. I basically know everything in the y direction except for time. But I'm ultimately looking for x. So although I know a lot about y, just because I have 2 dimensions doesn't mean I have to use both. So let's go and see. Well, in the x direction, the only equation that's really valid is our x equals, I'm going to write this a little smaller up top, x equals x0 plus vx0t plus 1/2 ax t squared. So I always start there, even though I know this equation simplifies down. I know that my ax is 0 and my x0 is 0. So this equation just tells me that x is equal to Vx0, but Vx0 is V0 cosine theta times t. Now, I know V0. I know V0. I know theta, but I don't know t, which means I don't have enough information just to work in the x direction. So I need a way to find t. So I know that there are equations in the y direction that have t. So the one in particular that we use a lot is the y equals y0 plus vy0t plus 1/2 ayt squared. Hey, what do you know? It's the same equation as the x one. Now, we don't have a 0 acceleration in this case, but we do know that our initial and final positions are 0 because it's at the ground. So I can rewrite this equation as 0 equals, and then Vy0 is V0 sine theta times t. And then Ay is negative g. So I'm going to write this as minus 1/2 gt squared by substituting in negative g and then just moving the negative out front. So this is where I'm going to start. Now, if I look at this equation, I know V0, I know theta, I know g, so the only variable I'm missing is t. So I can therefore solve this equation for time and substitute it in above. Now, fortunately, because I have a t in both terms, I can actually factor that t out. And I get V0 sine theta minus 1/2 gt times t. So I can split that up and say that t is equal to 0, and V0 sine theta minus 1/2 gt is also equal to 0. Now this is representing that there's actually 2 times that the object is going to have that same vertical position. So there, it's here and here, but I'm interested in this position over on this side. So now when I go to solve this equation, I can add the 1/2 gt to the other side. So V0 sine theta is equal to 1/2 gt. And then when I solve for t, I get that t is equal to 2 V0 sine theta over g. And so at this point in time, I actually have all that information. I can numerically calculate a value for the time that it takes for it to hit the ground. Now, I'm not going to do that because I only want to do one calculation. It's really important that you get in the habit of doing that because it will save you problems with rounding. It'll save you calculator mistakes because that's one of the most important things that happens. So I'm going to draw a little roadmap here. I'm going to come over here. I'm going to substitute in for my time up there. Now, I'm doing this non-numerically because we can learn more about it. You need to get in the habit of doing it non-numerically. Yes, it will be faster if you plug in numbers, but if you don't practice working these problems non-numerically, when you get a problem that has no numbers, if you haven't been practicing, it becomes painful and you make more algebra mistakes and things when you go through. So you really need to practice this process. Now, because I've run out of room, I'm going to erase what I have right here and rewrite that. So I found that t was equal to 2 V0 sine theta over g. So now that I substitute in, I get x is equal to V0 cosine theta times 2 V0 sine theta over g. It's important to show those steps before doing any simplifying, because once again, if you make a mistake while simplifying, they may not be able to track your work. And then I can combine some terms and simplify it down. I get 2 V0 squared cosine theta sine theta. I feel like there's some sort of double angle identity that could simplify that down into one term. I don't remember particularly, which might actually be helpful if you were doing some sort of analysis of the effect of theta on x would be useful for that. So whoever said that all those trig identities weren't useful in pre-calc, if you haven't learned them yet, you will. It's actually kind of fun, but tedious. But we have an ability here to kind of figure out what is the effect of changing variables on the range. So what this tells me is if I were to say double my initial velocity, because I have this square term here, if I double my initial velocity, I'm going to get 4 times the distance. So that initial velocity has a huge effect on how far that this can travel. I can also see that if I say went to the moon, which has 1/6 of the gravity of Earth, so 1/6 the acceleration due to gravity, that if I have 1/6 of g, I'm going to end up with 6 times the distance. So if you've seen the pictures of like the astronauts walking on the moon, they're kind of like bouncing. Their normal steps are like bouncing. And that's because the acceleration to gravity is so much smaller that any little liftoff they get gives them the ability to travel further than they would under Earth's gravity. And so we can learn that from this equation. We can see the effect. Now, it's harder to see the way this is written right now, the effect of angle. Well, angle has some really fun and interesting things, but what actually ends up happening, because it's a cosine and a sine, is it happens that if I have, there's some special angles. If I want to kind of hit this particular position, I can hit that position at lots of different angles depending on the speed. And 45 degrees is going to give me the ability to maximize this. And there's ways to mathematically prove that. But if I have an initial launch angle of 45 degrees, then that's going to give me my maximum possible distance possible for any particular speed. And then what's really cool is if I go equal degrees on either side, I may not go as far, but like if I go 60 degrees, I might not reach as far of a distance. I'll spend a lot more time in the air, but I'll hit this point right here. What's really awesome is you could use this equation to prove it, is if I did 30 degrees and I had an initial angle of 30 degrees, that actually I'm going to hit the exact same spot as if 60 degrees. It's just going to land earlier. And that's because they're both 15 degrees away from 45. So you get these symmetrical pairs. And once again, that's because of the parabolic nature of that function. So you're going to get kind of symmetry and the way kind of that the sine and cosines work together. So because the sine of 30 and the cosine of 30 are going to have the same product as sine of 30, cosine of 30, whichever, the vice versa. So that kind of works for this one. Now, if I actually wanted to go through and plug in numbers, I can. Numbers to me just get in the way. But, you know, numbers are values, and engineers care about numbers a lot more than physicists do. But if I wanted to, I would show my work properly. So I would show my numerical substitution of V0, which is 1.70 times 10 to the third meters per second, squared cosine of 55 degrees, sine of 55 degrees, all over 9.8 meters per second squared. Now, this G is the scalar value 9.8 meters per second squared. I originally substituted in a negative G. The algebra removed the negative, so if you plug a negative in here, you're going to get a negative position. So that's really silly. Also, make sure that you're in degree mode. Weird things happen when you switch back and forth between pre-cal and calculus and physics. Physics, we spend more time in degree than we do in radians. And if your calculator is set for radians, you'll get some weird, funky answers. And when you plug that in to a calculator, you get something like 2.77 times 10 to the fifth meters for the range. If you wanted to find the time it actually took using that equation was around 284 seconds. So had you wanted to find the time, or it asked for the time in a different part, plugging in values there would have given you that amount of time. So that position in that amount of time. So that gives you an idea of how to solve a very traditional type of problem. Your packet has so many more different types of problems because there are a wide variety of these. And these don't go away because when we get to other units, they like to do things like have a collision and then knock a block off of a table and it becomes a projectile. Or swing a rope in the air and the rope breaks and it becomes a projectile. So practice. We'll have lots of time to practice in class, and we'll see how things go. Have a good day.